Welcome everyone to our automotive update. My name's John. I'm with Javelin Technologies. I'm one of the directors of engineering for the 3D printing team here at Javelin. And today we've got back with us George Russell from Stratasys, and George is a segment leader for automotive in the Americas. So George's role oversees all major 3D printing customers in the automotive sector and helping them implement 3D printing. So George is going to share with us some of the great things he's seen out there. Hopefully they'll resonate with you, and we'll be able to help you guys take advantage of some of the new things that he's helping to develop. So George, without further ado, over to you.
Thanks, John. So again, apologies. This is definitely on my end. I'm actually, for the crowd, I ran late in a meeting, and I'm sitting in a McDonald's parking lot parasiting off their internet. So it's my issue, I'm sure, with the video feed. So let me just go through this. As John said, I'm the automotive segment leader for Stratasys. I have two counterparts, one in aerospace and one in medical. And what Stratasys has been trying to do is to segment our organization so that we focus on particular industries that use 3D printing in a particular way. So the automotive industry uses our printers a lot differently than the medical and the dental industry, and our idea is to form a team, sales, application, and working with our resellers closely, as I have many times with Javelin, to sharpen up our interaction with our automotive-specific customers. So thanks for your time today, and we'll start talking about how we're using additive across the automotive industry. The first slide you see there, these are some of the functional areas that our customers in automotive are using additive manufacturing and 3D printing. Functional prototyping has always been a very big one, rapid prototyping, but what's really happening in the automotive industry right now is a shift in focus just beyond the prototyping end of it, which is still very important to us, but we're finding that our automotive customers are really taking advantage of using 3D printing and additive out in the actual manufacturing spaces. So we're going to be talking about, as you see that, those bottom three on the left, jigs and fixtures, tooling, and surrogate parts today specifically. So I'll start out with jigs and fixtures and tooling. What you're seeing on the screen there is a typical automotive fixture. It's made out of aluminum. You can see all the complicated angles and really kind of a crude design that just gets this thing in the hands of the production workers. And the specific function of this fixture is to align the two glasses in the car so they're lined up perfectly with each other. And the aluminum fixture weighed about 12 pounds, very kind of difficult to manufacture, a lot of problems with it. You see the hoses flying all over the place there, and difficult for the operator to actually use. So this automotive OEM and Stratasys collaborated to come up with a new design that was based on an additive manufacturing production as opposed to traditional methods. So you can see already just from the difference between what you have here and what you have there, there's a much more ergonomic design. All the hoses are contained inside of the fixture itself. Much more easy for the operator to use, much more accurate, less fatigue out on the line when they're using it, and already they've come up with 3 or 4 ways to make this thing even better. So just a few numbers here. This fixture would probably cost about $5,000 to make, left and right side, and with the material used and the cost that we did with this fixture, about $1,600, and we were able to get it on the line about a week after we got the original data to do the redesign. So there's also, you can see, a high degree of integration of standard components. All the suction cups and gauges and everything that you see there are the exact same ones that were on the aluminum fixture. So we're actually designing it to protect some of that hardware, to integrate it, but there was no reason to order anything special for the additive fixture. And you can see the actual picture of it there. They let us take it off the line so we could take a better photograph of it. But you can see the weight savings, the time savings, and the cost savings. And that's what's really got the automotive industry excited, because they spend a lot of money on these kind of tools, and it adds a lot of lead time to get an assembly line up and running, or if you're going to make changes on the line or retrofit a line. These are the kind of things that add time and cost to get a new model through the production line. So we call it like the next frontier, really, of additive and automotive. Jigs and fixtures to hold and place and check and validate. I'm not sure who's on the line here, but I'm sure that all of you out there have dealt with jigs and fixtures if you're in any kind of manufacturing operation. Here's some examples of an automotive fixture. This is a headlight alignment and gap check gauge. Also things like emblem mounting. That's actually a BMW car there. And the original fixture that they used was plates of aluminum. They were heavy. They were not ergonomic. They were able to design something like this. And as I'll mention later, with 3D printing, complexity has no bearing on the cost of producing the part. You can see this is a tool that helps attach a bumper to the BMW, and you can see again the integration of electrical and mechanical devices inside the complex geometry of the 3D printed fixture. Things like fitting and cubing devices, and what happens out on the line is somebody comes up with a better idea. With the 3D printer in the plant, they're able to produce another fixture, another version of it, and by tomorrow they've got an even better fixture running on the line. Here's another example. This isn't strictly automotive. This is from one of our customers, Polaris. You see on the right there, this fixture is clamping a firewall for a snowmobile. What they found out was when they were shooting these parts in the injection mold machine, which was a very large, very expensive machine, they had to leave it in the machine longer than they wanted to, because if they put it out too soon, it warped. So someone had the idea, as their production ramped up, the managers are thinking they have to buy another injection mold machine because of the cycle time, and they figured out if they printed a fixture that you see there on the left, very complicated geometry, optimized for this job. They pull the part out of the mold or the injection mold machine much quicker, clamp it in a series of these fixtures, and they're ready to shoot another part. The fixture holds and keeps in place the integrity of the firewall and doesn't warp, and that saved them a lot of money in not having to buy another machine. But you can see from that geometry, if you had to machine that or cast it, or it would be very expensive to actually make that fixture. Here's some other inspection gauges. There's a lot of things that come in from suppliers that need to be checked really quickly to make sure they're fitting, or if they're not fitting on the car, to figure out whether or not it's the actual piece or something wrong with the car. There's a lot of this kind of fixturing being 3D printed now. You can see the complexity of the geometry. It's got to fit exactly to the sheet metal parts that you see there, and we're able to do that very quickly with 3D printing. All kinds of different vehicle assembly tools. I can't even tell you exactly what these do, but you see them all over automotive plants, and more you see them 3D printed. Here's another fixture for checking, complex checks fixtures. That's a very expensive fixture to make if you're gonna make it out of aluminum and machine it. And they were able to optimize the design and 3D print it very quickly and for much less cost. Some of the other things that we're doing is thermoform tooling. One of the benefits of a 3D printed FDM part is that it's porous. So you can make a fairly complicated thermoform tool, vary the porosity, which we have the capability of doing, and allow very quick manufacturing of tooling that will run on a thermoform tool. And here's an example of a very large one. I've got the guy's hand in there for scale. That's a full pallet size tool for actually transporting CV joints between plants of one of our automotive OEM customers, and to be able to quickly put a tool together that makes these kind of forms saves them a lot of money and a lot of time. Some of the other things that we're doing, for those of you that are more into the custom vehicles or composites, mandrels have always been a complicated thing to make. You see some examples there. We make what's called a soluble mandrel. Our support material dissolves in water in a wash tank, and what you can do is print the shape of the mandrel, put it in the wash tank, the interior dissolves out, and what's left is a very complicated composite part that would have otherwise cost a lot of money and a lot of time to make the mandrels to make that kind of geometry. Also, layup tools for composite materials. This is just a small example. Some of you may be involved in layup tools. You can print layup tools very quickly in our FDM technology, and some of our more advanced materials will stand up to the autoclaving that has to go on after. And we've been very successful with it, especially in the aircraft industry, but also now more and more in the automotive industry. So that's the jigs and fixtures side of the equation. I also wanted to talk about surrogate parts, and people often ask me, well, what do you mean by surrogate parts? So surrogate parts are parts that go into the plant for setup before the metal parts are available, or alleviate the expense of making metal parts. You see a casting there. You also see sheet metal parts down there in the bottom for welding. Some of the OEMs call them MTOs, or machine tryout parts, but the idea is to get parts in the plant well in advance of the plant having to go into production. This little slide here talks about the whole automotive design through manufacturing space. Traditionally, we've been in the circle above where the product design and engineering happens. As you can see in the lower circle, production concept and manufacturing engineering starts working hand in hand even through the product design. So the plants often need versions of these parts that are going to go through the plant so they can do a variety of different things, and that's what we're addressing with surrogate parts. And here's some examples. Like we printed this bumper. What you don't see on the bumper there on top is the B side, where all the clips are that attach it to the car. The plant wanted that way in advance of the actual part being ready so that they could start lining out their manufacturing processes. As you see it, what I'm saying there, how to handle it, how to place it, how to attach it, how many guys do you need to do the operation. All of those things can be lined out before the metal parts are actually available and get the plant in much better shape to go into production than it would have been waiting for those metal parts to be produced. Also, if you're taking an existing, if you see the BMW there at the bottom, an existing platform that's been redesigned into a whole different model, that's a lot harder than it sounds. And so what they'll do a lot of times is actually print the body panels that are going to go on the new design and check them in the plant to figure out how that adaptation could take place on the manufacturing side. Here's another example of a surrogate part. This is an instrument panel. So the idea here is to print not only the panel but also the carrier. And what they do is they use this to check and make sure that all the components that are going to go into the instrument panel actually fit, the tolerances are right, how they're going to assemble it, and make sure that the wiring is not going to be in the way, and line out a real good production process way before that instrument panel has been tooled up and actually available for them to test. So as soon as the guys on the engineering side are done, or say they're done with something as complex as an instrument panel, the plant can print it and start lining out their manufacturing processes and getting ready and solving problems way before they become a problem when the metal parts are available. Another big area is casting. For those of you who are casting in the casting business, a lot of times what happens is you need an as-cast model and then a machined model with your casting vendors and your CNC programs and your machining centers. So the idea here is to print both and then be able to line out your machining processes. What you see there is an actual cutting tool that's been 3D printed to test the tool paths without actually breaking an expensive head or breaking the machine tool itself while they're doing the testing on the casting. And then if you see a robot there, what some of our customers actually do is print in two pieces the casting model and fill it up with weight so that it actually is mass accurate for sorry, I just got a weird email that popped up on my screen. So that the robot is actually lifting something that's going to weigh and be shaped exactly right as the production piece. So I talked about machining centers. It's pretty obvious with the castings. The one that we've really been doing a lot of is weld teaching. Some of the OEMs are actually printing floor pans and entire upper structures of the body months in advance of that being available in metal, so that they can teach their welding centers, which is very complicated, and be able to anticipate and work out problems before the actual parts hit the plant. End-of-arm tooling, you can print a lot of this when you're doing weld teaching and lining out things, so you're not actually breaking or damaging the expensive end-of-arm tooling, which may not even exist at that point. So you can check how that's going to work at the end of the robot. And then, you know, there's really, once the car is, and I show this graphic here because a lot of times there are problematic areas of the car. If you look at the back of this vehicle, you can see where the fuel system, there's a door on the, your fuel door on the back quarter panel. There's a hose that goes to that. It goes down through the car into the gas tank. And we've actually had people just cut that part out of the car in CAD and print that part of it, put it up on a stand, and practice installing the hose to see what the problems are going to be in production. So really any part of the car that you're working with that you think you might have manufacturing problems. One of our OEMs had a lift gate that they couldn't figure out how to seal in CAD, and they printed it, and a problem that they had been trying to figure out for 6 months. Engineering and manufacturing sat down in the same room together with a 3D printed model of the lift gate, and in 2 hours they figured out how they were going to do it. So finally here, I'm talking about packaging. I don't know if any of you think about that, but packaging systems are becoming something that a lot of the automotive manufacturers are focusing on. They build a lot of these trays, very expensive to move parts around in the plant, and with 3D printing, they can actually print whatever part is going to be moved around well in advance of the metal parts being there, so they can start planning their packaging. One of our really good customers in the world is BMW. I've showed you a couple examples of their parts. They bought a very large Fortis 900 printer down in their plant in South Carolina in Spartanburg, just to print surrogate parts for packaging planning. The one you see there on the right is a kit box. These kit boxes can be very complicated. They ride around the assembly line with different parts that are specifically, these boxes are designed to hold the parts in place, and with either a robot or a human reaching in there in order and pulling out the parts that need to be assembled on the car. You can see how complicated that is there on the right, and how much it would cost to injection mold something like that. Companies are saving a lot of money, and we can optimize that design too with 3D printing. So speed and saving money and quality are the areas that they're looking at when they're putting these applications together. Here's another example with the CV joint. You've seen this tray before earlier. They actually made the tool for this tray, but even if they don't make the tool to do the thermoforming, they're 3D printing a lot of their parts so they can do the packaging planning. So just to summarize some of the things that we've just talked about, additive manufacturing 3D printing it allows our automotive customers to make tooling, jigs and fixtures, gauges, all those kind of things very fast, very flexibly, and very cost effectively. These new designed tools, because of the freedom that you have with 3D printing, you know, they're lighter, they're more ergonomic, and it encourages innovation and optimization of these tools. So I always wait for this bullet point, because a lot of you are thinking, well, we can't 3D print a lot of the tools that we have in the plant, and you're absolutely right. There are some tools, you know, a number of them that have to be metal. Either it's a striking tool or it's carrying the car down the assembly line. It goes beyond the capability of plastic, and we're not saying that every tool in the plant can be 3D printed. We're looking for that percentage of tools that are complicated geometry, that with new materials like the Ultem material I described before, all our nylon materials, you'd be surprised at how strong and how much weight and impact these things can absorb, especially if they're redesigned for additive and not just copied from the metal design. So as we add new materials to our product line, it also expands the envelope of what is possible to 3D print and be effective in the manufacturing processes. And it's really easy, not really easy, but the ROI on something like this, like when I showed you that first example of the quarter glass alignment fixture in the beginning, the ROI was very powerful on that, and the reason that we helped them with that one was to prove how much time and cost they could save. So I've worked with Javelin on many projects like this, where the customer says, okay, here's my tool, this is what it looks like in metal, and we'll take that tool, redesign it for additive, print it, and be totally transparent with how long it took to build, how much material's in there, so that our customers can compare and start understanding what the return on investment can be. And a lot of times the most tricky thing to do a return on investment on in the manufacturing environment is time. Time is the enemy of manufacturing. I mean, you know, there's never enough time, always compressed cycles, always things that come up that make situations, you know, big emergencies. If a line goes down, it's not like a prototype breaking in engineering and they have to make another one. If a line goes down and a machine goes down, a lot of times additive can come to the rescue and print things that get things back up and running quickly. So time is, and in the case of surrogate parts, as you heard me say before, they can work out a lot of problems up front that save a lot of time when it comes time to press that big button and start making cars. Very little infrastructure with our printers. I haven't actually talked about any printer itself, which may be surprising to you, because we're focusing on applications first, and then we figure out the right printer and material to do the job. But our printers, when you print in 3D printing, oftentimes there's a lot of infrastructure that you have to do to make rooms that are temperature and humidity controlled. Our largest printers are sitting right out on the production floor in many automotive plants without any special environment. And once we print them, to clean up the support material is basically setting it into a agitated tank, and the support material that you need with 3D printing melts away very quickly, and you're ready to use the part. Accuracy, durability, repeatability, all of those things are hallmarks of Stratasys 3D printers. FDM, and I didn't talk about the different processes, but fused deposition modeling by its nature prints with thermoplastics, especially those large parts that are open structures like bumpers and body panels. It is by far the most accurate and repeatable way to print some of those parts, and as well as tooling. If you're going to have a gauge, it's got to be accurate, it's got to measure correctly, and you might have to make 7 or 8 of them. You want them to come off the printer exactly the same way. Minimum post-processing, as I said, very easy to clean these parts once they come out of the machine and get them ready for use. And then we've got some new software that is making our 3D printers even more intuitive to use. A lot of people have said to me, well, you know, our guys are doing other jobs in the plants. They can't become 3D printer experts. And you'd be amazed at how quickly and how easy it is to pick up how to use the software. And these printers are designed not to be some science project that you have to calibrate and constantly babysit. They come out of the box and they're ready to use, and the operator does not have to be an additive manufacturing genius to get these things to work. And we're constantly trying to make it the ease of use and learning curve shorter and shorter. And finally, and our friends from Javelin, if you're interested in this, the cost barrier to put a fairly large printer into a plant, we've come out with a new line of mid-range printers, and the cost barrier to get started with additive, I think, will surprise you for the size of parts that we can make now, and the cost of the printers is getting more and more affordable. A lot of times what we'll do is put a smaller printer in the plant just to prove that it can do the job and people are getting value at it, and then a lot of times they'll graduate to the larger printers. So I know I went kind of quick because I ate up a lot of our time with my technical issues. I apologize for that, but we're going to go to the question and answer period, if that's okay, John.
That's great, George. If anybody out there's got some questions, feel free to type them into the questions panel, and we'll test George and see if he's got some answers there. There's none currently in there right now. I meant to mention it at the beginning of the presentation, but if you've got some questions, just pop them into that question section, and we'll go ahead and get them answered for you. Just while you're maybe typing those in, George is just south of the border, so he does get up to Ontario quite a bit, Windsor, Toronto, Kitchener, Cambridge, London, Waterloo. So if if you are in automotive and you would like to learn a little bit more and do that with some of George's expertise, that is something that we're able to organize.
And John, I'd just like to add to that, we're very excited about what we see happening with the automotive industry in Canada. I've been in the automotive industry my whole career, have spent a lot of time in Windsor and Toronto. The automotive OEMs like Honda and Toyota, Ford, GM, there's a lot of OEM plants in the Windsor and the Toronto area, and I've actually been up to Alliston a few times in the middle of winter with John and Doug from Javelin, and they're all making use of this technology. And like I said, our goal, especially in Canada where there's so many automotive suppliers, is to get people to understand how the OEMs are taking advantage of this technology and how it might benefit a supplier.
Hey, George, as usual, I think you've done a bang-up job. There's no questions, so you've answered everything. And since you've probably got a spot to go, and I don't want to test that Wi-Fi connection out any further, why don't we call that a wrap? And thanks very much, everybody on the line. And George, thanks again for your time today.